This 1/8 is not going to be long and it's not really hit much on the AP test, but it is a calculus topic, so I wanted to touch base with it. It's called the squeeze theorem. Squeeze or sandwich. Either way, this is what it's all about. It says, hey, if we've got three functions, check this out, f, g, and h, and f is smaller than g, which is smaller than h, near 1 point, except maybe at that 1 point. And the limits of, do you agree, f and h are my smallest and biggest, right? It's saying the limits of the smallest and the limits of the biggest one are the same. So they have to touch there, right? The limit of this one, let's say, is the peak of my fingers, and then the limit of this one would also have to be at the same point. Then it says the limit of the one in the middle would also have to be the same. Seems a bit redundant, but let's just draw ourselves a little picture. Let's just draw ourselves kind of what I just did. I'm going to say, hey, whoop, this function I'm going to call is f. Make sure the lower function is f, and I'm doing that because of this right here. F is less than some middle function g, which is less than some higher function h. So I'm going to say, oh, h is like this guy, and I'm going to have them touch there. Sorry, that was my phone. This one's going to be h. You guys, g has got to be in between it. So you can draw it however you want. I'm going to be like, woo, woo, woo. Let's go through this. It says for x near a, let's go ahead and say that this point is a. These are all matching up at this point a. And what are we going to say that limit is? They said that it's going to be L. So I'm just going to say off to the side, there's a little L. If f is less than h, and the limit for f and h is both L, if g fits in between them, its limit is also going to be L. Seems a bit redundant, okay? And here's how we even prove it. Guys, this is not going to be, this is not hit hard. So I just want to like expose you to it, and then we're moving on. So it says, hey, show that the limit of this equals 0. And you're like, ooh, this is a little insane. And correct me if I'm wrong, you guys. What happens if I plug a 0 in here? Am I going to be allowed to divide by 0? No. 1 over 0 is undefined. It doesn't exist. So I couldn't, I wouldn't be able to do any algebraic manipulation. But here's what we got to think about. What do we know about sine? What do we know about the sine graph? How big can sine get? On the unit circle, what's the biggest y value that we have? And what's the smallest? Okay, so am I good to say that the sine of x is sandwiched between 1 and -1? You comfortable with that? When we see this, we can even change this to say, all right, I also know that the sine of any angle, the biggest it's going to be is 1 and the smallest it's going to be is -1. So this is still a true statement. We just know the sine, no matter what that angle is always going to be bounded between 1 and -1. Then what our job is we've got to make this match the function that they gave us. And it's close. What is this thing missing that this thing has? An x squared. If I multiply this one by x squared, I get to multiply everything by x squared. Not I get to, I must. Right? If Henry go gets himself a caramel apple pop, he better be getting all of us a caramel apple pop. Am I right, people? Not only is it missing the x squareds that we just did, we got some limit notation. So let's exactly that. Let's write that. We're saying, all right, the limit as x approaches 0. We now know, oh, sorry, what would this turn into? Wouldn't that turn into actually, if I multiplied this one by an x squared, I got to multiply this one, it'd be a negative x squared then? Yeah. So we got a negative x squared there. Is less than or equal to x squared sine of 1 over x is less than or equal to, you got it. I multiplied that x squared to everything here. And now, you guys, we're going to plug in. Meaning, what is 0 squared? 0. What is 0 squared? What number is going to be between 0 and 0? If this function is greater than that but less than that, what will this value have to be? 0. So here's how the squeeze theorem works. We cannot do any more algebra to this. We're going to get some undefined thing. We can't do algebra to this. But if I know it's got to be bigger than 0 and also less than 0, this has to be 0. We squeezed it in between things that we do know. That's how the squeeze theorem works. So how I would put that is I just kind of bring this thing down. I mean, you could throw a 0 in the middle of that, but I'm just going to say, I don't know, this is some madness. And this is going to be less than 0, but also greater than 0. Therefore, the answer to this question, the limit as x approaches 0 of x squared sine of 1 over x is 0. And all you got to say is because of the squeeze theorem. Because of the squeeze theorem. If Cooper says sandwich theorem, fine. So again, this seems a little redundant, but I know that the cosine of x is never bigger than 1 or less than -1. No matter what happens to that angle, will it still be bounded between 1 and -1? Yeah, so I can go ahead and replace this with 1 over x is still bounded between 1 and -1. We're getting through it. So what is this missing that this has? An x. So if I multiply the first thing, the middle thing times x, everything's got to get an x. Mr. Biscuit says, I actually love writing the limit notation now, so I'm going to say the limit as x approaches 0. He got that from right here. And then I'm going to rewrite this statement having multiplied the x to everything. -1 times x is going to get me a -x. I have x cosine of 1 over x. 1 times x here gets me x. At this point, we plug it in. What's -0? And drawing your arrows, I think, will help you. -0 over there, +0. So what can we assess? Can we say 0 is less than or equal to x cosine of 1 over x is less than or equal to 0? So if we're evaluating that limit, if the limit of this has to be smaller than 0 but bigger than 0, what's the limit going to be? 0. So how to write that fancily is we're going to just say, okay, this is a little annoying. The limit as x approaches 0 of the function that they gave us, which was x cosine of 1 over x, is 0 because squeeze theorem. This one's not quite the same, but again, we're going to break down what we know. I know sine is bounded between 1 and -1. So let's do it. -1 is less than or equal to sine of x, which is less than or equal to 1. Is that what they gave me? Yeah. Nah, they gave me sine of x over x. So I got to say, all right, I got to divide this thing by x. And therefore, I got to divide everything by x. So now I'm going to say, all right, the limit as x approaches infinity. Interesting. This one I changed up on you a little bit. As x approaches infinity. And I'm going to write what I got. I've got a -1 over x. It's less than or equal to sine of x over x. And that's less than or equal to 1 over x. We don't know what's going on here. If you can recall, this is an oscillating function. What happens if I substitute in an infinity for x? What if I take -1 and I divide it infinitely many times?
You get 0.
You're basically going to get 0, right? So we get to replace that. That's going to turn into a 0. What if I take +1 and I divide it infinitely many times? I give this $1. We have $1 to split between everyone on the entire planet and then some. Is anyone getting any money? No, you're basically going to get nothing, right? So 1 divided infinitely many times is going to get me 0. So that's another way that we can demonstrate that the limit as x approaches infinity of this function, sine of x over x, is 0 because of that squeeze theorem or sandwich theorem. Before we get. All right, on 1-9. This is just saying we've now looked at limits in equations, tables, and graphs. We've done all of them, so they're just calling those multiple representations. Let's go ahead and put it all together. So it says g is a function that is increasing. So I like to kind of highlight things. On the AP test, because you don't get highlighters or anything, I'm a big circler. Like, all right, we're talking the function g. It's increasing when my x values are less than 1. Uh-oh. Was I supposed to have a different word there, I wonder? And the limit as x approaches 1 is 5. Which of these could represent g? Which of these could represent g? The limit has to equal 5. Do I care what's happening at 5?
No.
No, because that's the point. I'm caring what happens as we approach 5. So do I care, not at 5, looking at my limit as x approaches 1. I don't care what's happening at 1. So do you agree when this says when x is 1, my y is 3, that's not dealing with the limit. That's the point. So this part, this is just saying it's got the 0.13. That's not talking about the limit. What's this talking about around 1? This is saying this is the function for everything but 1. So this is the function, and then there's going to be a hole at 1. So we actually care about this part when we're talking a limit, right? So how would I evaluate the limit as x approaches 1 there? We're going to go plug a 1 right there for all my x's. What would that get it? Maybe we write that off to the side. The limit as x approaches 1 of this would get me what plus what minus what? Over something. 1 plus, yeah, all over? Yeah, 1 minus 1. Oh, silly us. Isn't that getting me 0 over 0? What do we have to do? Factor it. Toot or oh toot the top? Toot. So what multiplies to be negative 4 adds to be 3?
4 and negative 1.
4 and negative 1. Agreed, bud. So I'd say, all right, I'd have limit as x approaches 1, x plus 4, x minus 1. Why do I like that, Cooper? Look what the denominator was. That's nice, right? That whole is canceling out now. Now, what's my limit as x approaches 1?
1 plus 4.
Is?
5.
Is that what they wanted?
Yeah.
Yeah. So the test on this one is we're used to everything until calculus. We're always like, oh, when x is 1, bam, y is 3. That's the point. But limits are it's not what's happening at the point. It's what happens as we approach that point. And this is the function for every part of that graph except at 1. Bless you. So I'm digging 1. I'm digging it. What about as x approaches?
What would that not be?
Okay. So we're down with 1. What about on 2? As x approaches 1, are my x's approaching 1 in this option 2? Okay. Are my y's approaching 5? But does this have the point 1, 5?
Yes.
Do we care about that?
No.
Now I want my limit to be 5. So this limit does not exist, so I'm not down with 2. How about on number 3? Does the limit equal 5?
Yeah. 1, 2, 3, 4, 5.
Yeah. Are we down with that?
Yeah.
All right. Okay, guys. This one says, hey, the graph of G is shown. Which of the following could be a table for G? You guys, what's G of 4? I'm going to just throw that out there right now. What's G of 4? 1. Which of these tables has G of 4 is 1? C and D. I'm digging it. It's got to have the point 4, 1, 4, 1. This one does not. This one does not. Does this one have a limit as x approaches 4?
Yeah.
What's the limit looking like?
2.16.
Well, the limit's looking like from as I approach from the left and the right. It's looking like it's getting. You're right. It does look a little higher than 2, doesn't it?
Higher than 2.
Looks a little higher than 2. As I approach 4 from the left and the right, are these approaching 4? Are those approaching 4? Oh, we already got rid of A and B anyway. Are these approaching 4? Okay, my X's are all approaching 4, right? Can't rule those out. What are my Y's do we think doing? Are these two coming together at something a little bit bigger than 2, do we think? Yeah, Henry's saying, yeah, I agree. Don't let this throw you off. The limit's what happens as we approach it, not what happens at the point. But both of these Y values are bigger than 2. What are these? That's our problem over here. It's not bigger than 2, right? Answer is C. Let's see. On number 3, I have, which part do you think is a misprint?
The 2x plus 1.
There's 2x equals 3.
So that would need to be less than.
Okay.
Good call. So it says h is a piecewise function. The limit does not exist, you guys. Limit does not exist, which could be h. Yeah, let's go make this or equals to, people. So they want the limit to not exist. What would we have to analyze here? Does it matter that there's no point there? The point's undefined. But if there's a hole, meaning it's undefined, could the limit still exist? Yeah, so do we need to check both sides of 3 still?
Yeah.
Yeah, let's do it. I'm going to plug in a 3 there, and I'm going to plug in a 3 there. Do we need to get the same thing for that limit to exist? Yeah, let's do it. What did I get on top? What about on the bottom? 7. Does that limit exist?
Yes.
It exists, and they said that the limit doesn't exist. So what are we doing with 1? Crossing it off. And if you're wondering like what that notation would be, if I were to write that correctly, I would have said as I approach 3 from the left side of 2x plus 1, I got 7. That's how I would have done that notation there. If I were to approach 3 from the right side of 10 minus x, I would have gotten 7. How about on this table? The limit does not exist. Do we think the table, the limit does not exist? What happens as I approach 3 from the left side? Where are those y values going? What do you think? From the left, they're going to 7-ish? What about from the right? They're definitely not going to 7, are they? Like there is some kind of jump discontinuity. So are you cool with saying that one does not exist? Okay. Okay. What about as x approaches 3 on this graph? Does the limit exist or not exist? So I come in from both sides. My fingers are not together. It does not exist. Answer? D. Which could be a values for f? Here's my graph. What do I know about f of 1? Great. Do any of these tables not have that?
You also didn't.
Oh, nice.
Up again.
Did I? Answer's going to be A or B because it has the point 1, 7. What's going on with my limit? How about as I approach 1 from both sides? What's that limit going to be? 4. My limit's going to be 4. What's A looking like? Are those y values coming together at 4?
No.
Nah, fam. What about B? Yes. Those y values are coming together at 4. I'm digging B. So it'd be B only.